Factorizing a quadratic expression. Even though this is a quadratic expression because we have 3x squared, this can be factorized with just the generic idea of factorization. We have two terms and we can see common factors there. So look at the numbers first. What number divides both 6 and 3 evenly? That will have to be 3. So we'll keep the 3 at the front here. Now let's look at the letters. X squared and x. What letter divides both evenly? That will be x. So this 3x is our common factor for that expression. So now let's do the division, because factorization is division. 3x squared, the first term, divided by the common factor 3x. So what happens there? 3 cancels out with 3 because 3 divided by 3 is 1, and 1 times anything will be whatever comes afterwards. Now x squared divided by x, we know now is going to be just x, because that x on the bottom cancels with one of those x's on the top. Then we do the second expression, 6x divided by the same common factor, 3x. So we end up with 6 divided by 3 will be 2, and x divided by x is 1, and 1 times 2 is still 2. We could write 2 times 1, but that would still end up as 2. There is the expression. We can check it multiplying back, expanding it back to see if it goes back to the original expression. We could do that now. 3x times x, 3x squared. 3x times negative 2, negative 6x, which matches with the original expression. So final answer, the factorized form for that original expression will be 3x bracket x minus 2. Another quadratic expression we factorize now is this one here, and the difference is we have 3 terms. We have the term in x or a squared, the term in a or x, and the independent term, just the number. So for this type of quadratic expression, we will always try, we have to try, sometimes it's not possible, to factorize with 2 sets of brackets, because there is no one common factor like in the generic factorization, because a doesn't repeat in all terms. The numbers don't repeat either. 7 and 12 are not even coming from the same number. So what we know that is going to satisfy the top expression is starting with a in both brackets, because what we are doing here is multiplying. So a times a squared, that's satisfied. Then we are going to look at the independent term, including the sign, which in this case is 12, and we're going to try and find numbers that multiply to 12. So we are going to, of course, try to look for whole numbers. So there could be a list there. We could think the obvious 1 times 12, 2 times 6, 3 times 4, and that's probably it for now. Then what we're going to do is check check the middle number here, the middle because it's in front of a or in front of x. That number is going to give us the sum of these 2 pairs, or this pair that we are after. So let's check if any of them is going to give us negative 7 if we add them. 1 plus 12, 13, that's out. 2 plus 6, 8, that's out. 3 plus 4, 7. Well, that is out, but it's very close. So maybe what we have to do is allow for negatives. Negative 3 times negative 4 is still positive 12. So it does satisfy this condition that the product of the 2 numbers we are after is 12. Then if we test negative 3 plus negative 4 adding two negative numbers, we continue with the negative, and we have -7, which satisfies that second condition. So these two numbers are what we need to add here, -3, -4. The order wouldn't matter. We could have had a -4, a -3. So factorizing a quadratic that has 3 terms is always going to be a bit of a trial and error. You're going to list the possible numbers that multiply to the pink condition, which is the independent term, no x, no letter, no a, and then you're going to test one of those, all of the pairs, and find one that satisfies the other condition, which is the sum of those two numbers need to match the coefficient of x or a, the middle one. And another type of factorization for quadratics will be another quadratic that is not with 3 terms, just 2 terms, but very special, because what we see here is x squared and then subtract, take away 81. So this is what we call the difference of 2 perfect squares. What do I mean by that? Well, x squared, even in the way we read it, is the square of x. But 81 is the square of what? 9. 9 squared is 81. So again, this is the difference. That's how we're going to identify this type of quadratic expression of 2 perfect squares. So we are also going to have to factorize it with 2 sets of brackets. The first condition to satisfy is that x times x will give us x squared. The second condition to satisfy is using that 9, which is the square root of 81, as the second element. And then we need a plus and a minus. That's it. So always looking for the subtraction, so the difference of 2 perfect squares, and then separating them, like square rooting each one and using one pair with addition and one with subtraction. You can always multiply back and check if you are correct. So x plus 9, x minus 9, if you expand the whole lot, x times x, x squared, x times -9 minus 9x, then 9 times x, 9x, and 9 times -9, -81. Look at what happens there. The x squared is here, the -81 is there, and look how interesting, the -9x plus 9x is 0. They cancel each other out. That's why one of the signs need to be plus and one of the signs needs to be minus.